I'm Pranav, and I'll be doing this little video presentation about me and Bo's Project 4. So just as an introduction, we explored an unsupervised learning approach to estimate depth and pose, or ego motion, from a sequence of images. Um, we used SFM Learner, which is a paper that David Lowe's team at Google wrote, and they ended up publishing the code on GitHub, and we used that as starter code for this project. The goal of this entire project was to improve the performance, and by making changes to the loss function, or augmenting the data, or changing the network architecture. One of our first approaches was inspired by a paper that some people at GeoNet did, which used structural similarity metric, or SSIM, as a better indicator of determining the difference between two images than conventional methods. So the loss function was the first major change that we did. It's made up of three major components, which is the photometric loss, or the pixel loss, and the smooth loss. There's a third one, which is explainability loss, which was actually not used by the authors of the SFM Learner paper. So we won't be going into that. So pixel loss. Basically, the change that we did here was to compute the SSIM between the target and the source view. The goal is to consider the luminance, or the brightness, and the contrast and structure of the image, pretty much. And the reason behind that is that humans are more susceptible to these changes than slight pixel value changes. In other words, you could describe it as SSIM considering image degradation as perceived changes in the three criteria that we talked about than a conventional pixel by pixel approach. So this is the formula that we use to determine the pixel loss, and we use alpha is equal to 0.85 by cross-validation. There's also smooth loss. The point of using the smooth loss is to preserve image sharpness while also getting rid of random jitters in the image due to errors in prediction. It's also edge aware, so and it's weighted by the image gradient. So we end up getting a sharp yet smoothened image at the end. In terms of the network architecture, originally we attempted to use ResNet 50 instead of VGG, which is the network architecture that's used in the original code that's provided. Initially, the training looked promising. We were getting much better training loss, much lower training loss than VGG, but some of the downsides were that it took way too long to train. For example, VGG took 5 minutes per epoch, while ResNet 50 took 12 minutes per epoch to train, and I believe the entire training time was around 10.5 hours, which was a very long time to wait, and we didn't end up training the model for the entire 10.5 hours. We only trained it, I believe, for 3 hours. Then, apart from that, the biggest issue was that the architecture did not work well with the rest of the code. That meant that various other parts had to be changed, and we had an issue with actually running the testing pipeline. There was an issue with the expected model when we were loading the checkpoints, which we couldn't figure out, despite that we were using all the correct code that the same code that we had used to create the model was being used, but we couldn't quite figure out what was the issue. But at the end, we just decided to go back to the VGG model, and we continued to use SSIM loss. So this is a set of our initial results. We have 4 images. The color RGB images, and then on the right we have the result of our model. Um, it it is pretty good in terms of detecting objects, especially on the side of the road. For example, the stop sign here is very distinctly visible along with this little marker, as well as the McDonald's sign, which is visible here, though it's a little blurry. Um, Another interesting thing that stood out to us was the fact that how the lane markers ended up showing. Um, as you can see, there's a little hint of the lane markers. It could be an artifact, but we're not sure, but it's an interesting observation. In terms of the other challenges that we had, the biggest one was that it was very hard to run the code. It was very resource heavy, and I unfortunately lacked the resources, but Bo did. Bo actually had the resources to run, so it was a lot of like back and forth and cooperation between the both of us. Um, I was sitting here trying to help him fix an issue, and we were sort of debugging virtually, and it was sort of hard for me to run the code. Um, but it was, even though we did a lot of back and forth, I think it was successful because we ended up still communicating well with each other. Another issue was that the test set was really large, and we didn't get access to the subset of the test set until another classmate posted sequences 7 and 4 earlier today, and that didn't give us enough time to actually go ahead with the rest of the project. And hence, that's sort of the reason why we're missing a lot of the components. Finally, because the finals and last minute time crunch, it was just overall just hard. But thank you. This was a little presentation.